speed to market, their overall yields, and the efficiency of their manufacturing operations very significantly. About 2 or 3 years ago, we started taking the same concept and applying it to board assembly and system assembly as well. And we're working with several different customers, including tier 1 automotive electronic manufacturers, on building out these same capabilities for those industries too. And what we're seeing is that the same methodologies, which have been common now in semiconductor for a long time, also work very well in the electronics arena. Last year alone, we handled the data of over 70 billion devices, which gives us a very good visibility into the common threads, the common issues, and the common problems which exist both in semiconductor and electronics manufacturing today. And the way we do that typically is we have software which we install on equipment, assembly or test equipment in factories. We have servers deployed in all of the factories which are able to run edge analytics and take action through the systems that already exist at the various factories, whether outsourced or internal. And we can bring all of that data to the headquarters of our customers or onto the cloud, wherever they want to store it, in order to perform that type of analytics. And it's with that background that we're now able to take that same concept and try and apply it across the supply chain, across multiple different silos. So what is it that we actually do? We fundamentally ask 3 different questions. The first question we ask is good good, and is bad bad? In other words, if the testing process at the end of the manufacture of a board or the manufacture of a chip tells us that the chip is good, but in fact we determine through statistics or through some kind of analysis that this is not a good call, that's a quality escape potentially, right? This is a chip that's going to get delivered to a customer, it's going to get into that car, and it's going to cause that car to fail when it rolls off the line. But conversely, if every kind of signal that might predict problems is something that forces us to kill a board or kill a device, then we're going to get lots of false negatives, right? If the testing equipment tells us this is a bad part, but we actually determine statistically that it's a good part, this is an opportunity to improve efficiency and yield and so on, and lower the cost of manufacture for the people building the components which eventually make their way into that car. So those are 2 questions we ask. As good and as bad is bad bad. The third question we ask is how good is good? Right? A typical ECU consists of a PCB with multiple different chips in it from multiple different manufacturers. Now, all of those devices passed all of the testing criteria when they were tested individually. However, does anyone really know to predict whether or not various marginal issues with all of those components aren't adding up to create a marginal board which is eventually going to fail when this device gets into a car? So if we can take all of the data from all of the devices and all of the data collected from the board and put it together, correlate it together, run machine learning and so on in order to cluster and identify issues in that data, we can actually do a much better job of predicting which devices are actually going to work in the field and which are the devices which are going to fail. So one of the capabilities, for example, is the ability to correlate everything to everything. Take all of the measurements that we're getting from a board and all of the measurements that we're getting from a chip or from a system which contains that board or whatever combination, put them together and you can see where there's high correlations. If there's a high correlation, we can then go and identify situations like this, right? We have 2 measurements, one from a board, one from a chip. They correlate very well. But there are a bunch of points out here which are not fitting that line. When we look at them, we can actually see very often, because we get data about RMAs that are coming back from the customers, we can see the situations where those RMAs have actually a very clear signal here in the data, which we could have used to predict them in advance. Now, when we know that we have the RMAs, we can also know something else. If there are other points in here, right, which are also outside of that correlation, those are potential recalls. Now, if I have chip or board traceability, and I know where those boards went, into which vehicle, I can actually do now a proactive recall targeted to the specific vehicles that are going to exhibit the problem. I don't need to do a recall of millions of vehicles. Now, in order to do all of that, you're talking about huge volumes of data. Huge volumes of data, tremendous dimensionality. It becomes very difficult from a data science perspective, from an analytics perspective. And many of our customers are talking about including machine learning in their manufacturing processes, right? Not just in the car, not just in the ability to recognize things happening on the road, but also in manufacturing itself. And what we're hearing is that people are really struggling to implement that. I'll skip through this quickly. There's the terminology, right? Artificial intelligence is the overall topic of computers being able to do things that they weren't explicitly programmed to do. Machine learning is a specific statistical arena, and deep learning, which is typically associated with image recognition, video recognition, and so on, is a deeper part of that. So we're really focusing on machine learning in general. And when we ask our customers, are you using it, we hear some very interesting answers. I would say it's now, the first answer is actually very rare, right? We have customers who still say, yes, I've heard about machine learning, but I'm not doing anything with it. It's too complicated. I don't have data scientists. I don't have the budget. I'm using standard analytics. But I would say that that is now becoming a rarer occurrence in the industry. We have a lot of people who complain about this. Yes, I've got my data scientists. They're great at developing some algorithm or solving a particular point issue, but we've got no way of implementing this, deploying this across our entire manufacturing operation. And the third type say, yeah, they've managed to do one project or two projects and we've got it deployed and it works beautifully. But once we get beyond the third or fourth project, because of the ongoing maintenance of everything that they're doing, they're not able to continue to scale. There is, the reason for this is because the whole topic of machine learning is a complex topic for organizations to get their hands around. And what we're hearing from customers is, the process is complex. We need to learn. In order to learn, we need to gather all of our historical data. We need the systems that can do that. We need to be able to run the analytics on that. It takes data scientists weeks just to get the data that they need in order to run some kind of analysis. Then we need to connect that into business processes, right? If I've got something that can predict failure, I need to be able to prevent the parts that are predicted to fail from shipping. How do I connect that into the MES systems of all my manufacturers when my manufacturing is outsourced? Okay, it becomes a significant technical issue. And then, of course, once I have my model working and I've managed to deploy it into my manufacturing environment, how do I monitor it? The data science team spend all of their time continually monitoring the performance of the algorithms they've written to make sure that they're not making bad decisions because of some kind of change in the process and the manufacturing process. And of course, the manufacturing process changes all the time. And finally, if it does change, I've got to go through the whole process again. I've got to adapt my algorithm, I've got to regenerate it, I've got to regenerate my model, republish it, reinsert it into the supply chain, and this becomes a cycle. So if I'm running a machine learning team, once I've got 3 or 4 projects like this, it becomes impossible to manage, and it becomes a significant scalability issue for companies. This is a great diagram from a few guys from Google. You can see the link down here, talking about the challenge behind machine learning. Very often when I talk to customers about what they're doing with machine learning, I get asked the question, what algorithms do you have? Or which models do you use? Or what type of analytics do you perform with machine learning? But actually that isn't the challenge at all. A good data scientist, given a set of data, can come up with an algorithm that will find something interesting very, very quickly. The tools are available today and it's very easy to do. The problem with machine learning, and it came very clear from this Google article, is that it requires a tremendous amount of infrastructure to actually make it happen in a manufacturing environment, right? You need to be able to collect your data, validate that data, present it to the analyst, providing the tools to extract the features, the data, the raw data that will be fed into those algorithms, the analysis tools to actually do that work. And then, of course, out in the supply chain, out in the manufacturing level, you need to have all of the serving infrastructure and connectivity to systems to make sure that all of this connects together. So writing the algorithm is the easy part. It's the infrastructure that's actually challenging. So when you look at the kinds of infrastructure that we have, and I showed it before, when we have systems that go out to the equipment itself, the ability to execute analytics in the supply chain at the edge, and also to create models and so on and manage them centrally, what you actually get is a system that can answer very many of these kinds of issues. And it's something that's available today for the electronics and semiconductor segments. Hopefully in the future it will be able to spin out to additional players. And putting all of that in a central location now, and we're beginning to connect suppliers and customers together, it's a separate topic we can talk about at some stage, is going to enable the industry moving forward to really achieve the goal of significantly reducing the failures that are common. I think the microphone. Some examples of things we're doing with machine learning today. We have algorithms, for example, out there that are doing crack detection. This is really more deep learning, looking for cracks in PCBs and the influence of cracks on the components that are around them. We've got algorithms that are reducing system level tests. by predicting the outcome of the test based on the test data from the components and the boards themselves and the combination of those. And the ability to predict RMAs and returns, analyzing the causes of those returns so that we can better identify them in advance and prevent bad parts from being manufactured in the first place. So some key takeaways from the presentation. Although the automotive manufacturers and the tier ones will want to achieve extremely high quality, in the end they're really dependent on their component manufacturers, and this has been made very clear by some of those examples we saw from Audi, BMW and others. We believe that analytics across the entire supply chain is going to be key to solving those issues, and various different methodologies to do that are going to have to occur over the next few years to get over that issue. When you have that kind of level of analytics and those volumes of data and dimensionality of data, it's going to require machine learning, it's going to require infrastructure that can support in a scalable manner machine learning projects across organizations and between organizations. And we believe that in the end, companies, manufacturers of components, and even the cars themselves are going to need to invest in all of these kinds of infrastructure to enable this visibility, the sharing and trust between the different players along that manufacturing value chain. So that's it. If there are any questions.
How do you think about the cost versus what the cost of training, the infrastructure you need and all that versus what you get? So then trying to adjust whether you're actually going to do that, or do it with humans, or do it using ML?
Yeah, so basically the answer is with the volumes of data that are out there today and the amount of information, and think about it, it's not just the manufacturing data, it's even the in-use data, right? That also contributes to this. There's no way humans can do this at a scalable manner. So the company has to decide if they're going to do it at all. Now, I don't think, if you think 2, 3, 5 years down the road, I don't think anyone's going to be deciding not to do it, because the industry won't stand for it, right? The customers in the end won't stand for it. I can tell you, but in the end, this is a value sale, right? Even from our perspective, in the small world that we've worked in until today with semiconductor and electronics manufacturers, we sell subscription-based software. We need to prove that value every single year. The ROI needs to be there. I can tell you that in the semiconductor industry, we're already at ROI numbers of like 25-fold per year. And those are the kinds of numbers we're talking. The value is huge. It's there in efficiency, it's there in quality, it's there in, think about even brand reputation, right? Just the ability to say my parts are highest quality, they don't fail. That has tremendous value to a company.
Hi, yeah, here. Thanks for your good presentation. I'm a data scientist, so I'm more interested on what kind of machine learning, deep learning, platform or framework you use, and what kind of algorithm you mostly, use. Yeah.
Yeah.
Thank you.
We're not trying to invent any wheels when it comes to platforms. We have embedded within our system. We have embedded technologies such as Python, R, Spark, and so on. And we enable our customers to use many different types of existing machine learning tools that are out there to create their algorithms. But what we're doing is we're providing them that data very quickly, very easily, and very fast, right? Solving a big problem for a data scientist. And once you've written your model and you're able to translate that into, again, Python, R, or whatever, any of those standard technologies, we have the ability to deploy that and execute the model out in the supply chain. So we're actually agnostic to the algorithm and the technology that you're using.
Good, thank you.
Please join me in thanking Mike for
Thank you.